should be arriving soon. Okay, so it's a pleasure to have Scott tell us about 3D gravity.
All right, is this thing on? You can hear me? Okay, no objections. Yeah, so I want to start by thanking the organizers for the invitation. And I also want to take the opportunity to express my gratitude for the existence of the Bootstrap collaboration. Over the years, I've made a lot of friends and started projects and learned a lot of things here. So thanks to everyone that made that happen. Anyway, today I'm going to tell you about this project from a couple months ago, plus some work in progress with Lorenz Eberhardt at the Institute and Mengyang Zhang, who's an excellent grad student at Princeton. And I also want to highlight Mengyang's giving a gong show talk at Strings in a couple weeks, so check it out. Okay, so today, part of the motivation for this work is this old folklore that pure ADS3 gravity is somehow related to SL2R squared Chern-Simons theory. But at least as it stands recently, both sides of this duality are in their own right kind of poorly understood. And moreover, the status of the dual CFT is highly unresolved, I think it's fair to say. There's some ideas floating around about random CFT, but the status of the dual CFT does not really help clarify this question. So today, I'm going to, again, retreat to the gravity theory, discuss it in its own right, and I'll describe a precise reformulation of ADS3 quantum gravity in terms of this new TQFT, which has some unusual features that I'll discuss, and that we called Virasoro TQFT. And the main thing I want to emphasize about this reformulation is that it's actually useful. It trivializes some old calculations that appeared in the literature and lets us compute things that I would have no clue how to compute in the metric formalism. So the plan for the talk is the following. I'll start by reviewing the classical phase space of ADS3 gravity. I'll then move on, hopefully rather quickly, to discuss its quantization. And this will lead me to introduce this Virasoro TQFT. I'll then describe how, in practice, one goes about computing partition functions. If I have time, I'll describe some surgery techniques. And finally, I'll conclude with some examples, which are, after all, the main point of this. All right, so let's get started. It's a famous fact, going back to the 80s, that ADS3 gravity in the first order formalism, where the gravitational degrees of freedom are the Vielbein, which I write as EA mu here, and the spin connection. Here I write the dualized spin connection, because in 3D we have the Levi-Civita symbol, so this just has a single local Lorentz index. Anyway, in the first order formalism, I can use these gravitational variables to define these SL2R gauge fields, A and A bar. And here L, the quantity curly L that appears here, is just related to the cosmological constant. It's the ADS3 length. And the reason I call these SL2R gauge fields is because under diffeomorphisms and local Lorentz transformations, these gauge fields transform as SL2R gauge fields. And indeed, one can recast the Einstein-Hilbert action expressed in terms of these first-order variables in terms of two Chern-Simons actions with level k and minus k for these gauge fields A and A bar. Now, this correspondence has some issues. I want to highlight one in particular, which is that in gravity, the Vielbein should be invertible. In other words, the metric should be non-degenerate. In Chern-Simons gauge theory, there's no such non-degeneracy condition on the gauge fields A and A bar. So in principle, in the gauge theory path integral, you would be integrating over many field configurations that look very singular from the point of view of the gravitational theory. And the main upshot of this TQFT is that it solves this problem. It's sort of what it does for a living. There are other conceptual issues which I won't dwell on too much here, such as the fact that in gravity we gauge large diffeomorphisms, and in gauge theory we only gauge the infinitesimal gauge transformations. And moreover, in gravity the metric is a dynamical variable, and we're instructed to sum over topologies. And Chern-Simons is a topological quantum field theory that you can typically consider on some fixed background. So this seems very unnatural from that point of view. Okay, so let's get into it a bit more on the phase space.
Can I ask a very basic thing? So when you say whether the Vielbein should be invertible or not, The field configuration space, are you saying they're disconnected components, or are they just connected components?
There are
similar-
disconnected components, yes.
Okay.
I'll get into that in a bit more detail in just a sec. For that to be true, actually, it's important that I'm talking about SL2R, not like SL2C. OK, good. So consider Chern-Simons on some 3-manifold M, which looks like sigma times R, where sigma is some Riemann surface. You can consider a punctured Riemann surface if you want. It's not important. Then the phase space of the Chern-Simons theory on this 3-manifold is nothing other than the moduli space of flat PSL2R connections on sigma. So these are 2D flat connections. The time component essentially acts as a Lagrange multiplier. And this space, as anticipated by Xi's question, is actually a disconnected space with 2 times the Euler characteristic plus 1 individual components. And indeed, most of the gauge field configurations in most of these components correspond to very singular configurations in gravity. But there's a special component which is known as Teichmuller space. Let me call this T of sigma, and this is one of these components in this Chern-Simons phase space. Teichmuller space labels, like a given point in Teichmuller space denotes a specific hyperbolic metric, a smooth hyperbolic metric on sigma. And it turns out to be a fact, a theorem, that it is exactly and only this component of phase space in which field configurations can be uplifted to smooth 3D metrics. So you have some hyperbolic metric on sigma, but for gauge field configurations in this component, you can uplift those to smooth 3D metrics on the full manifold M. So the upshot is that the gravitational phase space, let me call that M grav, is just given by 2 copies of this Teichmuller space. T of sigma times T of sigma bar.
Scott, can you give an example of a flat connection that lives in the other disconnected components, or just intuitively?
I mean, a kind of trivial example would be A equals 0. I don't have a good, like from the gauge theory point of view, it's kind of hard to characterize these different phase space. It has to do with the topology of the maps from pi1 into SL2R. It's not I don't have a very intuitive description of it. Okay. So now that we know what the classical phase space is, let's discuss its quantization. And of course, given this statement, of course, what that means is that we have to discuss the quantization of Teichmuller space. Thankfully for us, this was considered in an extremely beautiful and prescient paper by Hermann Verlinde in 1989. And what he showed was that in considering this SL2R Chern-Simons theory, with a very particular choice of polarization, the Gauss law constraints on the wave function and the quantization are exactly equivalent to the Virasoro-Ward identities. And what that means is that the Hilbert space is spanned, in a sense I'll make precise in a moment, by Virasoro conformal blocks. On sigma. Say, you should think of sigma here as like an initial value surface in this canonical quantization. So the precise statement is that the gravity Hilbert space, let me call this H grav of sigma, is given by 2 copies of this space H of sigma. where H of sigma is the space of holomorphic Virasoro conformal blocks. And it will turn out that a complete set is given by the set where all internal weights in the conformal block, let me call them HI, lie above this C-1/24 threshold. And this turns out to be related to normalizability of these states. And let me just remark in passing that these are precisely the conformal blocks that appear in Liouville's CFT. Yeah.
The content of the theorem you just mentioned, does it say that anything that's not in Teichmuller necessarily lives to some singular configuration of metrics?
Yeah, I believe that is the statement.
Does that mean they also have infinite action or not really? Like, is that the reason you're allowed to exclude them from your path integral? Does that necessarily follow?
I'm not sure if that's the right way to think about it, to be honest. All I know is the result, which is that it's exactly this component of phase space where the gauge fields lift to smooth 3D metrics. But I don't know if it's, yeah.
Okay.
I don't know a stronger statement than that. Are there any other questions here? Well, it will depend on the surface sigma. So the Teichmuller space. Oh, sorry. The question was what kind of Virasoro blocks, like 4-point blocks, and the answer is that it depends on this initial value surface sigma. So these conformal blocks are functions on this Teichmuller space, which depends on the surface. Yeah, so I mean, whichever surface you're considering. Okay, but there's more to a Hilbert space than a vector space. You need to equip it with some inner product. So let's discuss that. Actually, remarkably, essentially the form of the inner product that I'm about to write down actually appeared in Herman's paper in 1989. What I'm going to write is a modern reinterpretation of it, but essentially all the ingredients were there, which is kind of remarkable. Okay, so in constructing an inner product for these conformal blocks, what we're after is some operation that takes two conformal blocks and returns a number. And if you think about it, there's an essentially unique thing you can do. So I'll write the conformal blocks like this. Let me just take a second to write this down and I'll unpack it. Okay, so F means conformal block. Sigma means the surface, so 4-punctured sphere, 1-punctured torus, whatever. Curly C up here denotes the channel. So when writing down conformal blocks, you have to specify a channel, which amounts to a pair of pants decomposition of the surface sigma, together with some choice of dual graph. And here, this vector of what are referred to as Liouville momenta, P, specify the internal conformal weights in the following way. So we write H as C-1/24 plus PI squared. And that will be, this is a convenient parameterization partly because of this, this fact about normalizability. So anyway, these conformal blocks, like I said, are functions on the Teichmuller space, which I haven't mentioned this yet, but that's also equivalent to the universal cover of the moduli space of the surface sigma. So anyway, if you want to get a number, one thing you could try to do is to integrate them over the Teichmuller space. So here I'm using M to denote these coordinates on the Teichmuller space, which again is locally equivalent to the moduli space. But we know from string theory this isn't on its own a well-defined thing to do. You need the integrand to transform like a partition function or correlator of a C equals 26 CFT. So we need some observable in a CFT with central charge C hat equals 26 minus C. So if these are 4-point blocks, then this would be some 4-point function. And anytime you have external punctures, then you actually have to tune the external weights to solve the mass shell condition. So if you have some external weight delta here, then you have external weight 1 minus delta here, just like in string theory. And then for the integration over the moduli space to be well defined, you also have to include the BC ghosts, as in string theory. So here, let me just put this here. I only know of one. So what we need is a family of CFTs that exist for all central charges, like arbitrarily negative central charges. I only know of one candidate, and it's known as time-like Liouville CFT, which is a cousin of space-like ordinary Liouville CFT, in that it is some non-compact solution to the crossing equations, but it exists for all real values of the central charge less than 1. And thankfully for me, Victor actually discussed this in his talk in the first week, so some of you might have at least seen this thing before.
Sorry, Scott, but at least when Victor discussed it, there seemed to be something weird about this contour choice that you know.
That's right. That's right.
So is this really fully, you know, kosher? I mean,
I think it's kosher in the sense that it solves all the crossing equations with that choice of OPE contour. You can imagine a different contour, say one that goes below this line of singularities.
It's like a regularization. You had to, you know, move a little bit away from what you naively think
That's
the
right.
spectrum would
That's
be.
right.
But
I mean, I think there are only really two possibilities consistent with unitarity. Sorry for everyone that didn't see Victor's talk. This might seem like a non sequitur, but so there's this dense set of poles on the real line in the OPE contour. So basically, if you want the OP to converge, you can either place it above or below the sequence of singularities. And I think above is a fine choice, in that it leads to crossing symmetric correlators, but below might also be fine. So maybe that's some ambiguity in this inner product, but I don't think you have that many options.
as a more kind of conceptual point, so
Yeah, sure.
Usually the procedure I would follow to quantize is to first write down the symplectic form on phase space, and then can do something like geometric quantization or whatever.
That's basically what Herman did in his paper, as far as I understand.
But he didn't know about the time like Liouville.
That's
CFT,
right,
presumably. So how does he? I mean,
He wrote some formal path integral that soaked up the Weil anomaly, which he did call Liouville, but of course, time like Liouville had not been discovered or discussed at all at the time. So that's what I mean when I say this is a sort of modern reinterpretation of his work.
But it still sounds like here there's some potential ambiguity. You can imagine some other family of CFTs to put there.
Perhaps, and certainly at special values of the central charge, you know, you could imagine putting a non-unitary minimal model or something there. That would be fine.
I'm just wondering whether how unique this thing is. I mean, because usually when I quantize a classical, you know, mechanical system, there's a ton of ambiguities. We can modify, you know, the symbolic form by something of order h bar and so forth. In quantum field theory, usually it's more restricted because of locality.
Indeed.
So here, you're not invoking any other principles. You know, just at level of quantization, sounds like there could be many ambiguities.
Yes, yes. Yeah, I don't disagree with any of that. Let me just say that if you take the results of Herman's paper at face value, this is essentially what he wrote down, starting from this geometric quantization. Okay, so up until now, essentially everything I've said could be interpreted as review. But one of our main contributions, I think, is to give a more useful presentation than this string world sheet looking integral. So we claim that this can actually be evaluated, and the inner product is in fact orthogonal, but not orthonormal. So it's only non-vanishing if all of the internal weights are the same. And there's some non-trivial weight function here, which I call rho, which depends on the channel and the Riemann surface, P1. And we argue, we have kind of three different arguments for this. I won't go over any of them in detail here in view of time. But this is, as we argue, the OPE density of the corresponding observable in the channel C in space-like Liouville CFT. So just to give a concrete example to try and make this a bit more explicit, consider the sphere 4-point blocks. So imagine you have some S-channel block. The external operators have to be the same because for them to live in the same Hilbert space, but the internal weights can be different. And this is equal to this delta function that sets the two internal weights to be the same. But there's this residual weight function where this is the Carty density, and this is essentially the DOZZ formula for the structure constants of Liouville and a particularly nice normalization that we like. So these are all explicit functions and defined in terms of these special functions that show up in the in Virasoro representation theory. Let me not say more than that. But I just want to emphasize that this is completely explicit, and in some cases you can even check this like numerically. As a side comment, I just want to emphasize, I think this inner product is useful, could be useful for Bootstrap purposes in 2D CFT. It kind of reminds me of that story involving harmonic analysis on the Euclidean conformal group, where there's this inner product between conformal partial waves on the principal series. So I think there's some more juice to be gotten out of this structure, but I won't talk any more about this today. Are there any questions about any of this so far? Okay, good. Now, one very nice thing about this story is that this Hilbert space carries in some additional richer structure, which is related to the fact that the conformal blocks transform nicely under crossing transformations. To use some fancy language, the statement is that this Hilbert space carries a unitary representation of the 2D mapping class group, the group of crossing transformations on the surface. And so the upshot is that consider, for example, some T-channel block. It can be expressed in a complete basis of S-channel blocks. All of which are normalizable with respect to this Hilbert space. So there's some explicit crossing kernel that writes this T-channel block in a complete basis of S-channel blocks, all of which have weights above this C-1/24 threshold, because you see this PS contour runs along the real line. And in fact, you can actually use these kinds of crossing transformations if you demand unitarity of this representation of the mapping class group. You can actually use this to derive the inner product that I wrote down there. So that's another argument in favor of it. And so the upshot is that this Hilbert space closes under crossing. So the quantization is independent of your choice of basis of conformal blocks. And this is, in fact, enough data to define a consistent TQFT. So let's take stock on what we've done so far. So we started with this PSL2R Chern-Simons theory. We then made what, from the gauge theory point of view, surely looks like an entirely arbitrary restriction on the phase space to focus just on this Teichmuller component. And then we quantized it, and that's what defines this TQFT that we call Virasoro TQFT. Yeah, the question was about this crossing kernel F, which is indeed some explicit special functions that appear in this representation theory of the Virasoro algebra. It's some completely explicit thing. Thanks for the question. And I think a kind of useful way to think about this TQFT is that it is related to Liouville CFT, the ordinary one, not the space-like, in a completely analogous way as, say, for some compact gauge group G at level K, the Chern-Simons theory is related to the corresponding G level K WZW model, CFT. However, perhaps as a consequence of this rather sharp analogy, it's in a few senses not a very conventional TQFT, like those that one encounters based on, say, modular tensor category. For one thing, the Hilbert space is infinite dimensional. This space of conformal blocks is infinite dimensional. And the spectrum is continuous. So the spectrum, say, of Wilson lines in this TQFT is continuous. And that's related, of course, to the non-compactness of Liouville CFT. Related to this is the fact that the trivial line, which would correspond to the identity in the dual CFT, is not really part of the spectrum. It never appears as an internal state. Okay, are there any questions about this?
So should we think of this Liouville as living on the boundary of your space?
You should think of it as describing like the edge modes in the same sense that the WZW model describes the edge modes of the Chern-Simons theory. But I should emphasize here that I'm going to say that this TQFT describes gravity in some sense. One shouldn't think of the Liouville CFT as the dual boundary theory for a variety of reasons. It really should be more in the spirit of this sort of duality. Okay, so this is actually moving faster than I anticipated, so that's good. Okay, so I've set things up, so I think we can move on to discuss partition functions. Partition functions. So the role in life of a TQFT is to compute partition functions on three manifolds. So suppose you have some three-manifold M, and suppose it has some disconnected boundary components. So the boundary of M is some disjoint union of Riemann surfaces. Then I want you to think of the partition function of the TQFT on M, which I'll call Z vir of M, as actually being a state that lives in the tensor product of the Hilbert spaces associated with each boundary. And to make this statement a little bit more concrete, what that means is that the partition function is some linear combination of products of conformal blocks for each boundary component. So in practice, how do we compute these? The main technique, as Witten taught us for Chern-Simons theory, for example, is surgery. So to take your manifold M and cut it along some surface in the bulk. So now you have two pieces. You split M into two pieces, M1 and M2. By doing the cutting through the bulk, you introduce a new boundary. And so there's some shared boundary component between these two smaller pieces, M1 and M2. Then the partition function on M is simply given by the inner product of the partition function on these smaller pieces. The notation here may be a bit confusing. So, this is some state in the Hilbert space of the boundary components of M1, including the joint boundary component, and this is some state in the Hilbert space of the boundary components of M2. Here I'm only taking the inner product in the Hilbert space of the joint boundary, the cutting surface or splitting surface. So this is still some state that lives in this Hilbert space. Good. So this is basically how it works. You have to be careful in this story because of these unconventional features to only cut along surfaces for which the Hilbert space is well defined. At a practical level, this means you cut along 2D surfaces that are themselves hyperbolic in the 2D sense. So if you cut along a sphere, there should be at least 3 operator insertions. If you cut along a torus, there should be at least 1, and then any higher genus cutting is fine.
Since you have time, could you do more drawings?
Yeah, okay, yeah, sure. Okay, so just to, here's an M. Let's say there are some external operator insertions traversing through the bulk. For example, just to give an example of M, I'll make this cutting, since I have time, I will discuss this cutting a bit more explicitly. You can imagine cutting along some surface. This is a bad example, actually. Cutting along some surface, okay, ignore the color assignment, through the bulk like this, just very schematically. I'll make this concrete, a bit more concrete in just a second, since we have time.
When you write z as a function of m, when the data of m, does it come with a hyperbolic structure?
Not necessarily. Yeah, just as a state, I don't think I need to specify it. If you want to write the partition function, say, as a function of the moduli of the boundary surfaces, then you would need to specify that. But as a state, I don't think you need to specify the hyperbolic structure.
Wait, then I'm confused. What is a function of? I mean, I thought that these are functions of the complex
again,
structure,
you should think of this as some state. You could project to some state with fixed moduli on the boundary surfaces. I think of that like, the position basis for the wave function. But as an abstract state, I don't think you need to specify yeah.
But M needs to admit a hyperbolic structure.
Yeah, exactly. In particular, if you're going to take this inner product, then it's important that you're integrating over the Teichmüller space. So it needs to admit some hyperbolic structure. Okay, so the main technique that we found useful goes in the math literature under the name of Heegard or Heegard splitting. So let me start, just for simplicity, by discussing some closed three-manifold M. Almost all the examples I'll discuss later will have boundaries, but this is just to sort of illustrate the idea. Then it's a non-trivial fact that M can be written as the union of 2 handle bodies. So I'll say what these are in a second. So I use this notation S sigma to denote a handle body, which is some Riemann surface with the cycles filled in the bulk, or with some choice of cycles filled in the bulk. So this is, maybe I'll write the word, handle body. And so it's a non-trivial fact that closed three manifolds admit a decomposition into two handle bodies, perhaps up to some modular transformation acting on the boundary. So here, gamma is an element of the mapping class group of this boundary surface, which is called the splitting surface. When I first learned about this, it seemed very unintuitive, to be honest. But the way to think about it is another non-trivial fact about three manifolds is that they admit a triangulization. To obtain the handle bodies, you imagine puffing up the triangularization. And that sort of, if you picture it in your head, it's clear that that defines some handle body. And then the closure of the complement of that triangularization is also a handle body. And that sort of decomposition is exactly this Heegard splitting. Now, it's sort of a well-known fact that the gravity partition function on handle bodies is given by the identity block. Sorry for the density of the notation here. And so the partition function on the full three manifold M is given by the expectation value in the states prepared by these handle bodies, which are identity blocks, of the representation of this mapping class group element on the Hilbert space. And so in practice, what that means is that this is some linear combination of these crossing moves that act on this boundary splitting surface. So this is literally some integral over these F symbols. Now, you might complain because I told you that, I actually didn't emphasize this. I implicitly referred to the fact that only the states with conformal weights above this C-1/24 threshold are normalizable with respect to this inner product. In particular, that means that all conformal blocks with weights, internal weights below this threshold are not normalizable. So in particular, the identity block is not normalizable. And that's simply because this integral over the Teichmüller space diverges. You can see that there are singularities near these degeneration limits. So you might complain that there's no reason this should be finite, and indeed, generically, it need not be. But it should be finite whenever M is hyperbolic as a three-manifold, because those are configurations for which Einstein gravity admits a classical solution. So the heuristic is that this is finite for sufficiently complex elements, gamma, in the mapping class group. And that should exactly correspond to the case that M is itself hyperbolic. But actually proving this, characterizing the gammas for which M is hyperbolic, is actually a non-trivial thing to do. But anyway, this holds up in the examples we consider explicitly. Okay. Any questions about this? Okay, good. So of course, in 3D gravity, for the purposes of holography, we don't care so much about closed three manifolds. We're more interested in the case with asymptotic boundaries. So this Heegard splitting procedure needs to be generalized in some way. The same picture holds, this cutting through the bulk, but the ingredients that you need are slightly more complicated than handle bodies. So in the case of asymptotic boundaries, which after all is our main interest in holography, you replace the handle bodies in the preceding discussion with what's known as a compression body. I'll describe what that is in just a second. So the way to think about that is you start with some Riemann surface, you fill it in to get a handle body.
Sorry, I think I'm a bit lost.
Yeah.
What is the symbol U, that union with an index gamma? So
That means
have two-
identified up to the action of this mapping class group element. So I do a modular transformation on on the boundary of one of the handle bodies, and then I glue them along their boundary. So you should think of these as being identified. So these are filled in, you know.
Yes.
You do a modular transformation. So here's some SP4Z transformation, for example, and then you identify the boundaries. Of course, if I just identified them without doing any modular transformation, then I get the expectation value, I get the norm of the identity block, which is infinite. So that can't be a hyperbolic 3-manifold. You need to do some modular transformation on the boundary.
Sorry, what's the simplest possible picture where this all this construction could be visualized?
I think I'll describe some explicit examples in a second that'll make it a bit clearer. Maybe the canonical example would be the splitting of the 3-sphere into two tori, two solid tori. So this is S3. So you split S3 into the union of these two solid tori. I'm kind of struggling to draw the dual one, but you probably know what I mean. They're identified on their boundaries. Yeah, you should think of it as you have a donut, and then through the hole of the donut, there's a donut in the dual channel. And then they're identified along their boundaries, and this is S3. And this is not hyperbolic, but it's
Identified where? In the circle that they touch?
along the boundary, along the T2 boundary. So this is the union of two solid tori up to a modular S transformation. And so the partition function as a standard in TQFT is this identity element of the modular S matrix. This makes sense in RCFT, but it doesn't quite make sense here, which is related to the fact that S3 is not hyperbolic. I'll describe some more concrete examples later, which I think might make it clearer.
You mentioned the SP4Z just earlier, but
Yeah.
it's okay. But in your paper, you say
Yeah,
that's not.
let me not get into that here. I won't be talking that much about the mapping class group. the
But
sum over the
just a
mapping
kind of
class
a
group.
basic point. This mapping class group is still generated by the elementary crossing moves that we usually go between two different pair pairs decomposition. Is that correct? I'm assuming.
You mean like the Dane twists along the cycles?
Well, that's a different way to
Characterize it.
To characterize it.
Yeah, yeah.
I
I think in the higher genus handle body case, the relevant mapping class group is what's known as this handle body group, which is strictly bigger than the SP2GZ.
Okay, but I'm just asking whether, the usual crossing moves, which is the sphere 4-point
Oh, I see
crossing
what you
and
mean.
torus 1-point
Yeah,
crossing,
yeah.
that's enough to generate this entire group.
Yeah,
right?
yeah. I think that should still be true here.
But you're telling me that if I just write down the elements as matrices, they don't generate exactly SP to GZ, but something different.
Yeah, that's right.
So should I think of this Virasoro TQFT as vanishing on S3 because S11 is 0 for the
Well, is it 0 or is it infinity?
I thought it's 0 because there's only support above.
You can deform the contour in the S transform. I think it's just a kind of ambiguous thing.
I see.
Which is related to the fact, of course, that S3 is not hyperbolic.
I see.
But
if
the
it were
way I
hyperbolic,
would
there
think
would
about
not
it
be
is
this
this,
ambiguity.
it's just outside the scope of the TQFT.
Okay, thanks.
Okay. All right. Right. Okay, so we're discussing these compression bodies. You start with a handle body, so you take this Riemann surface, fill in some cycles, and then in the interior of the handle body, you drill out another Riemann surface. So now what you have is a configuration with two sigma boundaries. There's the outer one and the inner one, because you've drilled out this handle body in the interior. So topologically, what this is has gone under the name of the Euclidean wormhole, although it's usually not drawn this way, which has the topology of sigma times an interval. Okay? And then to form the most general compression body, you degenerate some of the cycles on the interior Riemann surface or the interior compression body that you've drilled out. So for example, I could degenerate this cycle in the bulk. And so what I have now is a surface with one outer boundary. In this example, it's this genus 4 Riemann surface, and potentially multiple inner boundaries. So this has two genus 2 inner boundaries. So this is some multi-boundary wormhole, but let's just call it a compression body. And the terminology we use for this is CG, which denotes the genus of the outer surface, and G1 through Gn for the genus of the inner Riemann surfaces. So the idea is that you can always cut 3 manifolds into these sorts of multi-boundary wormholes. And then what you're tasked with is to compute the partition function on these compression bodies. And the way that works, I think the discussion can be summarized briefly as the follows. So suppose we have this compression body with these two genus 2 inner boundaries. We insert a complete set of states with respect to the Hilbert spaces of these inner boundaries. And that will prepare a state in the Hilbert space of the outer boundary. So the basic idea that maybe it'll be useful to see some explicit examples shortly is to do surgery into these compression bodies. Then you insert a complete set of states. In the Hilbert spaces of these inner boundaries, that creates some state for you, or some linear combination of states in the Hilbert space of the outer boundary. And then you take the inner product. Because remember, in this picture, you're cutting the manifold into the 3-manifold M into 2 pieces like this, and then you identify them on their outer boundaries. So that's the basic idea. Are there any questions about this? Okay, well, before discussing some explicit examples, let me review the basic proposal. So the proposal that we arrive at from this sort of reasoning is that the gravity partition function on some fixed topology M, so here I'm not yet summing over topologies, is related to the mod square of this TQFT partition function. Okay, this pen is running out. But we have to sum over elements of the boundary mapping class group. So let me write that as. But I told you that in gravity, the bulk mapping class group has to be, is gauged. So you have to mod out by this mapping class group of the bulk that preserves the boundary components. So that's what I mean by this mapping class group M dm. And just to remind you, mapping class group of some space M is the space of diffeomorphisms modded out by those continuously connected to the identity. These are, for the 2D boundaries, these are like the modular transformations. And then we act on M with these boundary mapping class group elements. And the conjecture that has held up in all the examples we're able to consider is that this is always finite for M hyperbolic. As an aside, it's not obviously ill-defined if M is not hyperbolic. In some silly examples, it is, but it's not totally clear when this is finite, or what the meaning would be for M non-hyperbolic if this is finite. What is the interpretation? Okay. Yep.
Missing something very basic. So when you say, do you fix M or do you fix these boundaries?
Yeah,
you are
it's
doing
bit
a path
confusing.
integral, right?
In principle, I'm fixing M, the bulk topology.
Just the topology, but not M, not the...
Yeah, yeah. And then in principle in gravity, we want to sum over M with some fixed boundary dm. I'm not talking about that here, but in principle, one should do it as well.
So here you still need to do a path integral over the
Yeah,
matrix.
yeah, exactly. There's still some additional sum over topologies, which I'm not discussing.
So this is about evaluating Einstein-Hilbert on manifolds that don't satisfy necessarily Einstein equations?
No, for now this is all, I'm assuming M is hyperbolic, so it solves Einstein's equations.
Okay, so this is a technology for evaluating the action.
Yeah.
And then I still need to sum over...
Yeah, that's right.
But we need to also sum over solutions that are not hyperbolic, right?
It is believed that that is the case. And the status of that is still very much up in the air. There's some specific proposals for the case of torus boundary. But a calculation hasn't been done yet. I mean,
but how could it not be the case? I mean, it's always, we always sum over everything, right?
Right. Well, let me just say that in principle, this technology is well suited to the on-shell case, and it's not clear when it makes sense off-shell. Okay, let's discuss some examples. Yeah, okay, good. The first one I'll consider is this 4-boundary wormhole. So let's recall from last year's Bootstrap, actually, Tom's lectures. Tom very nicely described in Bootstrap 22 this Gaussian ensemble of CFT data and its relation to semi-classical ADS3 Einstein gravity. To briefly summarize the upshot of that discussion, there is a calculation of the on-shell action of this 2-boundary wormhole, which I'll draw like this. So each boundary here is a 2-sphere. There are 3 operator insertions that traverse the wormhole. 1, 2, 3. The on-shell action of this 2-boundary wormhole was computed, and it was shown to be equal to this C0 gadget. We put mod squared, which was then taken to define the variance of the structure constants in this Gaussian ensemble. You know, you could compute more general things, you know. Let's say there's some external operators. So this was computed, and it was shown. Again, this is in semi-classical gravity, so I'm talking about on-shell actions and potentially one-loop determinants. This was shown to be given by the Liouville partition function on sigma squared with some funny identification between the moduli of the two sides. And in this Gaussian ensemble, this was equal to the average of the product of CFT observables. Let me call this G of sigma, the correlator on sigma in the CFT, in this Gaussian ensemble. Now, this ensemble was only crossing invariant on average. And it was clear basically from the beginning that there were non-Gaussianities needed in order for internal consistency of the whole story. But we had no clue how to compute them in gravity. So for example, sort of the simplest generalization of this you could imagine is this configuration with 4 asymptotic boundaries. These are all 2 spheres. And you imagine the defects connecting them in this way, so that it corresponds to some connected contribution to the 4th moment. So let me label these 1, 2, S, 4, 3, 3, 2, T, T, 4, 1. Let me call this M. And the idea was that this, if you could compute the partition function on this thing, it might tell you about the following 4th moment. That is needed for the consistency of this whole ensemble story. So we can compute this in the TQFT. It's quite straightforward. And we apply this Heegard splitting technology. So the basic idea in this example is to split along this surface in the bulk. So I cut along this bulk surface, which is a sphere with 4 operator insertions. 1, 2, 3, 4. 1, 2, 4, 3. And then the TQFT partition function on this wormhole is given by the expectation value of the partition functions on these 2 compression bodies. So I cut along a sphere with 4 punctures, so these states are in the Hilbert space of the 4-punctured sphere. That is, there's some combination of sphere 4-point blocks. So in particular, we have combinations that look like this. I'll describe what these drawings mean in a second. So here, this is a cartoon meant to denote a 3-ball. So whose boundary is a 4-punctured sphere. And in the interior, I carve out 2 smaller 3-balls, and I connect the defects in this way. So this is 1, 4, 2, 3, T. So this is like the right compression body. And over here, I have 1, 2, S, 4, 3. This is like the left compression body. So to compute, so this is just going to be some T-channel block. This will be some S-channel block. And then I take the inner product to compute the partition function on this thing. And after the dust settles, what you get is the following explicit expression. I'll write it down just to show that it's some concrete expression. So this C0 thing shows up because it appears in the inner product. Same with the row. And also this F symbol that I wrote down earlier. Shows up. Essentially because I'm taking the inner product between the T and S channel blocks. All right, this is inverse. And you can actually simplify this expression somewhat. You see the bulk topology has some tetrahedral symmetry, which is completely obscured by this representation. But you can rewrite it in a more symmetric looking form. So you see this is just the square root of the product of all the C0s corresponding to these boundary spheres times this object, PS, P3, P4, PT. And this is the 6J symbol of this quantum group UQ SL2R, whose appearance from this point of view is kind of mysterious and not well explained, I think. Question, Pedro?
Yeah, I have a naive question. So, what about what is the semi-classical limit of this expression?
Yeah, very good. So you can take the semi-classical limit where you scale all the weights with C and take C to infinity. It's actually known that this 6J symbol exponentiates. So let me just omit the labels. Times the volume of some hyperbolic tetrahedron whose dihedral angles are specified by the weights in some specific way. So this computes, this shows that the on-shell action is up to these C0s given by the volume of this hyperbolic tetrahedron. Did that answer your question?
I guess I'm a little bit confused about, again, if we don't sum over the neighboring metrics, what's the meaning to keeping such very quantum expressions with all the prefactors and so on, since...
Yeah, at finite C, I kind of agree. Like, there's no reason you should talk only about a specific topology. In principle, you should sum over all of them. But it is curious, as we'll see, that these expressions at finite C for a fixed topology will always agree with the average of the CFT data in this ensemble. But I agree, it's a very quantum thing that we don't really have any right to talk about on its own from the point of view of gravity.
Just a comment and question. So about Pedro's question, I would say that just if you just do the pathing over GR and do the compute the Feynman diagram, you're supposed to recover this answer.
At the level around a given topology.
Yeah.
Yeah.
Yeah. So it's a non-trivial. It's a non-trivial.
That's
statement.
true. That's true.
I have a question that I meant to ask earlier. When you wrote the inner product, there's a timeline Liouville, but then you just have this density of states formula. The timeline Liouville is no longer needed after that point?
The time like Liouville appears in this worldsheet expression for the inner product, but indeed we argue that it can be specified entirely by this delta function with the rho, so it's not needed.
So if you had to replace the time Liouville by some other family of CFTs, so
presumably you would get a different answer, and it's not clear whether that answer would actually be unitarity. Would be consistent with unitarity of this representation of the mapping class group.
So that kind of
I think that's one argument in favor of this, definitely. Yeah. Okay, so let me just say that then if you square this and use this to define this fourth moment, I guess I wrote it earlier. This is actually exactly what's needed for consistency of this expression. You can see this by taking the product of two 4-point functions, expand one in the S channel and the other in the T channel. In the Gaussian ensemble, the product of OPE coefficients that appears would vanish. But if you use this, you get the same answer as you get if you expand and just say both in the S channel. And I want to suggest the possibility that this is, there's this recent story about the JT gravity plus matter matrix model, and there are these chord diagrams. And the 6J symbol for the classical group SL2R was the chordic vertex of that of this 2D gravity theory. So there's some sense in which, at least for these kinds of diagrams, 3D gravity is like a Q deformation and square of JT gravity plus matter. Just for fun, and since I have order 10 minutes, I'll draw one more example of this sort, just to put forward, just to further suggest this analogy with JT gravity, which is this 6-boundary wormhole. So I'll just draw the diagram and write the answer, just to show that it has some simple form. So for this class of diagrams, I always connect the defects in this cyclic way. 1A2, 2B3, 3C4, 4A5, 5C6, 6B1. Now to compute this thing, again, I split. And this time I can actually split along a 3-punctured sphere. So I can split along this surface, and I essentially cut it into 2 of these 4-boundary wormholes like I had earlier. So from that point of view, it shouldn't be surprising that the result you get is equal to, again, the product over external C0 factors. Let me avoid writing them. Times this product of 6J symbols. And this, again, is exactly consistent with this analogy with JT gravity plus matter, where there are these diagrammatic rules. And essentially, every time you have a crossing, a chordic crossing like this, you get a factor of the 6J symbol. It also agrees with the required 6th moment for consistency of this Gaussian ensemble, say if you average a product of 5-point functions, or 3 4-point functions. So I think this is the right answer from a variety of points of view. And as one final example, just because it's a bit more fun, although the connection to holography is less clear, you can talk about 3 manifolds without asymptotic boundaries. And a nice class of examples is furnished by what are known as hyperbolic links. So for example, you can take a knot. I'll draw a simple example here. This is the figure 8 knot, it's sometimes called 4,1. Embed it in S3, and then the complement is hyperbolic. So this is some, from the point of view of ADS-CFT, very bizarre looking thing to talk about, but it's well defined as a hyperbolic 3-manifold. And you can use the same sort of logic to compute the partition function. So you could imagine splitting, say, along 4-punctured spheres like this, and taking the inner product. In view of time, I won't write the explicit representation of the partition function. It involves some integral of the 6J symbol. But what you find in this semi-classical limit is that this again exponentiates. So you have this expression, you evaluate it by saddle point in the large C limit, and you get the that it exponentiates to the volume of this knot complement. This is some very specific number, 2.02988, dot, dot, dot. So yeah, you can start going kind of crazy fast. There's a lot of things you could consider. But I think this is a nice sort of family to think about. Okay, I have 2 minutes, so I'll just conclude with some final remarks if there aren't any questions. Okay. So the first is that in this work, we've extended this correspondence between 3D gravity partition functions and averaged CFT quantities. Let me just write CFT stuff. We've extended this correspondence to finite C. And the meaning of that is a bit mysterious to us. And it begs for a more unifying description that captures all these non-Gaussian corrections to the CFT data. One might imagine something like a matrix model for CFT statistics. Another that I alluded to earlier is the finiteness of this TQFT partition function. It would be nice to prove on very general grounds that when M is hyperbolic, this thing is finite. It would also be nice to understand when, if M is not hyperbolic, this thing is well-defined. There's also this volume conjecture that the last couple of examples I presented were starting to get at. This is usually presented in Chern-Simons, but here it would be nice to prove that the semi-classical limit exponentiates to the volume, or if there are asymptotic boundaries, the renormalized volume of M. You could even refine this with a one-loop determinant coming from like the Selberg trace formula on M. Obviously, the sum over topologies is sort of looming over this whole discussion. I don't have much to say about this, but it would be nice to think more about, and in particular in this case of closed three manifolds, you can imagine ordering them by their hyperbolic volume and perhaps summing over them. There are accumulation points in the space of volumes, but if you're interested, we can talk more later. I think there's a sense in which that can be dealt with. And finally, it would be good to understand the relation to these simplicial or combinatorial state sum models. This is actually how we started to think about this. There are these models for Chern-Simons theory where you triangulate the three manifold into tetrahedra, and so it relies on a sort of simplicial description of the manifold, and then you sum over states. There's some prescription to sum over states in the TQFT to compute the partition function. For reasons related to the non-conventional features of this TQFT, that didn't really work here, but it would be nice to understand this relation in more detail. Okay, so with that, I'll conclude. Thanks for your time.
So there's a conjecture or speculation that the Liouville CFT itself can be due to a particular interpretation of 3D gravity where the sum over topology collapses to a single term that is a hyperbolic three manifold with let's say a geometry boundary that is invariant under the action of the mapping class group.
Yeah.
Can you comment on the status or evidence for that?
Yeah, I think it basically works as you described. It's related to the partition function of Liouville on some non-orientable surface. And indeed, it's invariant under the bulk mapping class group, so it seems to have all the ingredients for what you
Sorry,
described.
what do you mean non-orientable? I mean, just on ordinary surface. I mean, the bulk is constructed by taking the surface times interval
And then doing some fixed point free involution.
Yeah.
Yeah. Yeah. It's been a while since I've thought about it, but the status of it is that the partition function on these twisted eye bundles is equal to some Liouville partition function on a non-orientable surface.
Is that a consequence of the conjectures we made here, or is it an independent thing?
Yeah, that's a good question. Certainly the relation to the ensemble description is not clear. It follows from the technical ingredients, like this splitting and so on. But it's not obviously related to any of the other conjectures.
You say it
you've
follows
mentioned.
from the
Yeah, I mean, that's how we
splitting
computed it.
So let's say in the genus 2 case, you say you do this compression body construction.
Yeah.
And the genus 2 partition function of Liouville, when you write it as integral over the Coulomb blocks, you say that that's actually a consequence of your Haggard or the splitting formula.
Yeah. Yeah. It involves the conformal blocks of torus with a cross cap, where you do this involution. Say in the Z2 case.
Oh, the torus with a cross cap.
Yeah.
And additional insertions of some vertex operators? Like you have to glue them in some way.
Yeah. I can't remember. Let me not comment on that right now.
Okay, but basically the upshot is that based on your conjectured formula for this Virtuosity QFT, you would say Liouville CFT is the dual of this specific interpretation of 3D gravity.
That's what it sounds like. I want to avoid giving that impression more generally.
So the finite C results is hard to interpret. Does any simplification happen for finite C but large quantum numbers, like Cardi style type, that you might be able to give interpretations to?
Well, let's see. The quantum numbers labeling the external states.
Yeah, like large momenta. Or
That's kind of a novel limit in CFT, right? Like the limit of large external dimension fixed. Yeah, it's a good question. It's not something we've really thought about. I'm not sure if it simplifies in any way.
Okay.
Usually we consider the large internal weight.
Yeah, but usually things simple like your 6J symbols kind of simplify.
Yeah.
Stuff, right?
Yeah.
You might be able to get.
It's a good
some
question.
sort of
Yeah,
gravity.
I don't have much more to say about it than that.
So one way to understand this average of CFTs is like some coarse graining due to semi-classic.
Yeah.
So here it's a finite C, and so
That's what I mean about the interpretation being a bit more confusing. It doesn't seem to be related to any effective coarse graining of UV degrees of freedom in the semi-classical limit, because it's just some partition function at finite C. But I mean, presumably there are large corrections coming from other topologies. But it still is surprising that on a fixed topology that the result is so cleanly related to these average quantities.
Well, if there are no more questions, let's thank Scott and go for lunch.